The universe has a birthday. After decades of measurements, refinements, and heated scientific debates, cosmologists have converged on a number that defines everything about cosmic history. 13.8 billion years. That is how long ago the Big Bang occurred. That is how much time has passed since space, time, matter, and energy burst into existence. The precision of this calculation represents one of humanity's greatest intellectual achievements, but getting here required overturning assumptions, reconciling contradictions, and pushing measurement technology to its absolute limits. What makes this number even more remarkable is that different methods using completely different physics arrive at the same answer. The universe is revealing its age through multiple independent voices, and they all tell the same story. Think about what we are claiming. We live on a planet orbiting an ordinary star in an ordinary galaxy, and yet we have calculated when everything began. The audacity of that claim should not be lost. How can beings confined to one tiny corner of space and time possibly measure the age of all existence? The answer lies in reading the messages encoded in light, in understanding how gravity shapes galaxies, and in detecting the faint radiation left over from the universe's fiery birth. Every photon carries information. Every galaxy preserves a record. The cosmos itself is a vast archaeological site, and we have learned how to read its layers. But this number, 13.8 billion years, was not always the accepted answer. For most of human history, the universe was thought to be eternal, unchanging, and infinite. Then, in the early 20th century, observations began revealing something shocking. The universe is expanding. Galaxies are rushing away from each other. If you run that expansion backward in time, everything converges to a single point, a moment of beginning. This realization transformed cosmology from philosophy into physics. Suddenly, the universe had a history. It had a starting point. And if it had a beginning, it had an age that could, in principle, be calculated. The first serious attempts to measure the universe's age came in the 1920s and 1930s, when Edwin Hubble discovered that distant galaxies are moving away from us. The speed at which they recede is proportional to their distance. This relationship, now called Hubble's law, provided the first tool for calculating cosmic age. If you know how fast galaxies are moving apart and how far apart they are, you can calculate how long they have been separating. Run the clock backward, and you reach the moment when everything was in the same place. The math is straightforward. The measurements, however, were not. Hubble's early estimates placed the universe's age at less than 2 billion years. This created an immediate crisis. Geologists had already determined that Earth itself was older than 2 billion years. Rocks and minerals on our planet contained radioactive elements that decay at known rates, and those decay chains pointed to an Earth age of at least 3 billion years, possibly more. The universe could not be younger than the rocks inside it. Something was wrong. Either the measurements of cosmic expansion were incorrect, or our understanding of radioactive decay was flawed, or the entire framework of an expanding universe needed to be reconsidered. Scientists faced a paradox that threatened to collapse the emerging picture of cosmic history. The problem lay in measuring distances to galaxies. Hubble had used certain stars called Cepheid variables, which pulse with a brightness that depends on their intrinsic luminosity. By measuring how bright they appear compared to how bright they actually are, astronomers can calculate distance. But Hubble did not know that there are two types of Cepheid variables with different intrinsic brightnesses. He was mixing them together, which systematically underestimated distances. If galaxies were farther away than he thought, then they were moving faster than their apparent speed suggested. A faster expansion rate means less time has passed since the Big Bang. The calculations were yielding ages that were too young because the distance measurements were too small. This error persisted for decades. Throughout the middle of the 20th century, cosmologists grappled with an embarrassing situation where their best estimates for the universe's age ranged from 2 billion to 10 billion years, depending on which measurements you trusted. Different teams using different methods arrived at wildly different answers. Some measurements suggested the universe was barely older than Earth. Others pointed to a cosmos twice or 3 times that age. The uncertainty was not small, it was enormous. The age of everything was uncertain by a factor of 5 or more. This was not precision, this was barely educated guessing. Several things had to happen before the picture cleared. First, astronomers needed to understand the different types of distance indicators in space and calibrate them properly. Cepheid variables were just the first rung on what is called the cosmic distance ladder. Each rung depends on the previous one. Measure cepheids in nearby galaxies, and you can calibrate brighter objects like supernovae, which can be seen at much greater distances. Use supernovae to map the expansion rate across billions of light years. Each step introduces potential errors. Each step requires careful cross-checking. Building a reliable distance ladder took most of the 20th century and required observations from increasingly powerful telescopes, both on the ground and in space. The Hubble Space Telescope, launched in 1990, revolutionized distance measurements. Named after Edwin Hubble himself, the telescope could observe Cepheid variables in galaxies tens of millions of light-years away, with unprecedented clarity. A key project in the 1990s involved measuring Cepheids in distant galaxies to pin down the expansion rate of the universe. The team, led by Wendy Friedman and collaborators, observed hundreds of Cepheids and calibrated the distance scale with far greater accuracy than ever before. Their work reduced the uncertainty in the cosmic expansion rate from nearly a factor of 2 down to about 10%. The universe's age estimates began to converge. At the same time, cosmologists were pursuing a completely different approach to measuring the age of the universe, one that did not rely on distances or expansion rates at all. They were studying the oldest stars in our galaxy. Stars burn hydrogen into helium through nuclear fusion, and the rate at which they burn depends on their mass. Massive stars burn hot and fast, exhausting their fuel in millions of years. Small stars burn cool and slow, potentially lasting trillions of years. The smallest, faintest stars that are still burning are called red dwarfs, and they set a lower limit on the universe's age. The universe must be at least as old as its oldest stars. But there are even older objects than red dwarfs. Globular clusters are tight spherical collections of hundreds of thousands of stars that orbit galaxies. The stars in these clusters formed together very early in cosmic history, and they share the same age. By studying the colors and brightnesses of stars in globular clusters, astronomers can determine how long they have been burning. The technique relies on understanding stellar evolution in exquisite detail. As stars age, they change color, move through different stages of brightness, and eventually exhaust their fuel. The exact path a star takes through this life cycle depends on its mass and chemical composition. By the 1990s, careful studies of globular clusters suggested they were between 11 and 13 billion years old. These ages came from detailed computer simulations of how stars evolve, combined with precise observations of star colors and brightnesses in multiple wavelength ranges. The oldest globular clusters set a firm, lower limit. The universe could not be younger than 11 billion years. This provided a crucial consistency check on expansion-based age estimates. If measurements of cosmic expansion suggested an age younger than the oldest stars, something was deeply wrong. For a while, there was tension between the two methods. Some expansion measurements gave ages around 8 or 9 billion years, while the globular clusters insisted on at least 11 billion. The contradiction had to be resolved. Here is where another measurement technique entered the picture, one that would ultimately provide the most precise determination of the universe's age. This method involves studying the cosmic microwave background, the faint radiation left over from the Big Bang itself. When the universe was about 380,000 years old, it cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, space was filled with a hot plasma of charged particles that scattered light in all directions. The universe was opaque. After this moment, light could travel freely through space. The universe became transparent. The light that was released at that moment has been traveling through space ever since, and we detect it today as microwave radiation, coming from all directions. The cosmic microwave background, often abbreviated as CMB, is the oldest light in the universe. It carries information about the conditions in the early universe encoded in its temperature and the tiny variations in that temperature across the sky. These variations are incredibly small, just a few parts in 100,000, but they represent the seeds from which all structure grew. Regions that were slightly denser than average eventually collapsed under gravity to form galaxies, stars, and planets. The pattern of hot and cold spots in the cosmic microwave background is a snapshot of the universe in its infancy, and that pattern depends on the age, composition, and expansion history of the cosmos. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, known as WMAP, to map the cosmic microwave background with unprecedented precision. The spacecraft spent 9 years measuring the temperature variations across the entire sky in multiple microwave frequencies. The data revealed an intricate pattern of spots and structures that matched theoretical predictions with stunning accuracy. By analyzing this pattern, cosmologists could extract fundamental parameters of the universe, including its age. The WMAP team announced their results, and the number that emerged was 13.7 billion years, give or take a few 100 million years. This was a breakthrough. The cosmic microwave background method did not depend on measuring distances to galaxies or understanding the life cycles of stars. It was completely independent, yet it agreed remarkably well with the other methods. The expansion rate measurements were converging on ages around 13 to 14 billion years. The oldest globular clusters were at least 11 billion years old, consistent with a universe that is 13.7 billion. The different lines of evidence were all pointing to the same answer. The universe was revealing its age through multiple channels, and the story was consistent. In 2009, the European Space Agency launched an even more advanced satellite called Planck. This mission mapped the cosmic microwave background with higher resolution and greater sensitivity than WMAP. Planck observed the sky in 9 frequency bands, allowing scientists to separate the primordial signal from foreground contamination caused by our own galaxy and other sources. The Planck team spent years analyzing the data, modeling the physics of the early universe, and extracting cosmological parameters. In 2013, they announced their results. The age of the universe, according to Planck, is 13.82 billion years, with an uncertainty of only about 40 million years. This represents a precision of better than 1%. Think about what that means. We know the age of the universe to within 1%. That is an extraordinary level of certainty about something so vast and ancient. The number 13.82 billion years is not a guess. It is not a rough estimate. It is a measurement based on physical laws, careful observations, and rigorous analysis. Multiple independent methods have converged on this value. The expansion rate of space, the ages of the oldest stars, and the pattern of radiation from the early universe all tell the same story. The cosmos is 13.8 billion years old, and we can measure that age with confidence. But how exactly does the cosmic microwave background tell us the age of the universe? The answer lies in understanding the physics of sound waves in the early cosmos. Before atoms formed, the universe was filled with a hot plasma where photons, electrons, and protons interacted constantly. Pressure waves traveled through this plasma, creating oscillations in density. These are essentially sound waves moving through the primordial material. The scale of these oscillations depended on how far sound could travel in the time between the Big Bang and the moment when atoms formed. That distance is called the sound horizon. The sound horizon sets a characteristic scale in the pattern of temperature variations in the cosmic microwave background. When we map these variations across the sky, we see a pattern of hot and cold spots with a particular angular size. The largest hot and cold spots correspond to regions that were exactly one sound horizon across when the light was released. Measuring the angular size of these spots allows us to calculate the physical size of the sound horizon, and that size depends on the age of the universe when the microwave background formed. If the universe was older at that moment, the sound horizon would be larger. If it was younger, the horizon would be smaller, but there is more information in the pattern. The cosmic microwave background shows not just the largest spots, but also smaller scale variations. These correspond to harmonics of the fundamental sound wave, like overtones in a musical note. The relative heights of these harmonics depend on the composition of the universe. How much ordinary matter is there? How much dark matter? How much dark energy? Each component affects the sound waves differently. Ordinary matter increases pressure and enhances the oscillations. Dark matter contributes gravity but does not interact with light. Dark energy affects the expansion rate and changes the geometry of space. All of these factors leave imprints on the pattern of the microwave background. By measuring the pattern precisely, cosmologists can solve for all of these parameters simultaneously. The result is a comprehensive model of the universe that specifies its age, composition, expansion rate, and geometry. The Planck satellite measured the cosmic microwave background so precisely that it could determine not just the age, but also that the universe is flat, meaning its geometry follows the rules of Euclidean space. It is made of about 5% ordinary matter, 27% dark matter, and 68% dark energy. It is expanding at a rate of about 67 kilometers per second per megaparsec, and it is 13.82 billion years old. This number represents the time since the Big Bang, the moment when space itself began expanding. But what does that actually mean? Time itself is part of the universe. It did not exist before the Big Bang, at least not in any conventional sense. Asking what happened before the Big Bang is like asking what is north of the North Pole. The question does not have a meaningful answer within our current understanding of physics. Time and space emerged together at the Big Bang, and the age we calculate is the duration of time that has passed since that moment. Every second, every year, every billion years of cosmic history is contained within that span of 13.8 billion years. The early universe was unimaginably hot and dense. In the first fraction of a second after the Big Bang, temperatures exceeded trillions of degrees. Matter and energy were interchangeable. Particles and antiparticles appeared and annihilated each other constantly. The fundamental forces of nature behaved differently than they do today. Gravity, electromagnetism, and the nuclear forces were possibly unified into a single force. As the universe expanded, it cooled. Symmetries broke. The forces separated into the distinct forms we observe now. This all happened in less than a second. By the time the universe was a few minutes old, it had cooled enough for protons and neutrons to stick together and form the first atomic nuclei. This era, called Big Bang nucleosynthesis, produced hydrogen, helium, and trace amounts of lithium and beryllium. The proportions of these elements depend on the density and temperature of the universe during those first few minutes, and they match what we observe in the oldest stars and gas clouds. This is another independent confirmation of the Big Bang model. The elemental abundances we measure today were set in the first minutes after the universe began. For the next 380,000 years, the universe remained too hot for atoms to form. Space was filled with plasma, and light could not travel far without scattering off charged particles. Then the temperature dropped below about 3,000 degrees, and electrons combined with nuclei to form neutral atoms. This moment, called recombination, released the light that we now detect as the cosmic microwave background. The universe became transparent for the first time. Light could finally stream freely through space. That light has been traveling toward us ever since, redshifted by cosmic expansion, and it reaches us today as microwave radiation with a temperature of just 2.7 degrees above absolute zero. After recombination, the universe entered a period often called the Dark Ages. Stars had not yet formed. Space was filled with neutral hydrogen gas, but there were no sources of light. Gravity slowly pulled matter together into the first dense clumps. These clumps grew over millions of years, becoming denser and hotter as they collapsed under their own weight. Eventually, the cores of these collapsing clouds reached temperatures high enough to ignite nuclear fusion. The first stars were born. This happened when the universe was only a few 100 million years old, less than 5% of its current age. Those first stars were massive and short-lived. They burned hot and bright, producing heavy elements in their cores through fusion. When they exhausted their fuel, they exploded as supernovae, scattering those heavy elements into space. The next generation of stars formed from gas enriched with carbon, oxygen, iron, and other elements. Over billions of years, this cycle repeated countless times. Stars formed, burned, exploded, and seeded space with heavier elements. Galaxies assembled as gravity pulled billions of stars together. Our own Milky Way galaxy formed about 13 billion years ago, just 800 million years after the Big Bang. It has been growing and evolving ever since. The Sun and Earth are much younger than the universe. Our solar system formed about 4.6 billion years ago from a cloud of gas and dust that contained elements forged in earlier generations of stars. That means the universe existed for more than 9 billion years before our planet came into being. For more than twice as long as Earth has existed, the cosmos was already full of galaxies, stars, and planets. The universe has a deep history that extends far beyond the history of our world. We are late arrivals to a very old cosmos. Understanding this timeline required piecing together multiple lines of evidence from different branches of physics and astronomy. The expansion rate tells us how much time has passed since space started expanding. The cosmic microwave background shows us the universe at age 380,000 years and encodes information about the physics that governed the early cosmos. The oldest stars and globular clusters set lower limits on cosmic age. Observations of distant galaxies show us what the universe looked like billions of years ago, because light takes time to travel across space. Each method provides a different window into cosmic history, and they all have to be consistent. For decades, they were not entirely consistent. Different measurements gave different answers, and the uncertainties were large enough that cosmologists could not be sure whether the disagreements were real or just measurement errors. The Hubble constant, which measures the expansion rate, was particularly contentious. Different teams using different methods reported values that disagreed by factors of nearly 2. This uncertainty translated directly into uncertainty about the universe's age. If the Hubble constant was large, the universe was young. If it was small, the universe was old. Getting the right answer required measuring the Hubble constant precisely. The Hubble constant is expressed in units of kilometers per second per megaparsec. That means for every megaparsec, roughly 3 million light-years, of distance between us and a galaxy, that galaxy is moving away from us at a speed given by the Hubble constant multiplied by that distance. The current best measurements give a value around 67 to 70 kilometers per second per megaparsec, depending on which method you use. There is still some disagreement between different measurement techniques, a tension that cosmologists are actively working to resolve. But the values are much closer together than they were decades ago. If you take the Hubble constant and invert it, you get a rough estimate of the universe's age. The inverse of 67 kilometers per second per megaparsec, after converting units appropriately, gives about 14 billion years. This is called the Hubble time. It is not exactly equal to the universe's age because the expansion rate has not been constant over cosmic history. The universe has been accelerating its expansion for the past several billion years due to dark energy, and before that, it was decelerating due to the gravity of matter, pulling everything together. The actual age depends on the full expansion history, not just the current rate, but the Hubble time gives a good ballpark estimate, and it matches the more precise value of 13.8 billion years, derived from the cosmic microwave background. The discovery that the expansion of the universe is accelerating came as a shock. In the late 1990s, 2 teams studying distant supernovae found that these exploding stars were fainter than expected. Since supernovae of a particular type always have the same intrinsic brightness, their apparent brightness tells us their distance. The supernovae were farther away than they should be if the universe were decelerating as expected. This could only mean one thing. The expansion of space is speeding up. Something is pushing galaxies apart faster and faster as time goes on. This mysterious force is called dark energy, and it now appears to dominate the universe. It makes up about 68% of the total energy content of the cosmos. We do not know what dark energy is. The simplest explanation is that it represents the energy of empty space itself, a concept called vacuum energy or the cosmological constant. Einstein originally introduced the cosmological constant into his equations of general relativity to allow for a static universe, then abandoned it when Hubble discovered cosmic expansion. Now it appears that Einstein was right to include it, just for different reasons. Vacuum energy pushes space apart, and that effect has become dominant in recent cosmic history. The existence of dark energy changes the age calculation. If the universe had been decelerating throughout its history, its age would be about 2/3 of the Hubble time, closer to 9 billion years. But the presence of dark energy means the universe has been expanding faster than it would have otherwise, especially in recent epochs. This stretches out the timeline. The acceleration counteracts the earlier deceleration, and the net result is that the universe is actually older than the simple Hubble time would suggest. When you include dark energy in the models and match them to the cosmic microwave background data, you get 13.8 billion years. Dark energy makes the universe older than it would be without it. Dark matter also plays a role in the age calculation. Dark matter is invisible material that interacts with ordinary matter only through gravity. It does not emit, absorb, or scatter light, which is why we call it dark. We know it exists because galaxies and galaxy clusters move in ways that cannot be explained by the gravity of visible matter alone. Stars orbit galaxies faster than they should. Galaxies within clusters move faster than the visible mass can account for. Gravitational lensing, the bending of light by gravity, reveals the presence of far more mass than we can see. All of these observations point to vast amounts of invisible matter surrounding and permeating galaxies. The amount of dark matter affects the expansion history of the universe and therefore its age. More dark matter means more gravity, which slows expansion more strongly in the early universe. This changes the relationship between the current expansion rate and the total age. The cosmic microwave background is sensitive to the dark matter content because dark matter affects the growth of structure in the early universe. The pattern of temperature variations depends on how much dark matter was present when the microwave background formed. By measuring that pattern precisely, Planck determined that dark matter makes up about 27% of the universe. This value fits consistently into the age calculation. So the age of 13.8 billion years depends on understanding the universe's composition and expansion history. The calculation involves general relativity, which describes how gravity shapes space and time. It involves thermodynamics and nuclear physics, which govern the behavior of matter and energy in the early universe. It involves quantum mechanics, which determines how atoms and light interact. All of these pieces fit together into a coherent model called the lambda-CDM model, where lambda represents dark energy and CDM stands for cold, dark matter. This model has become the standard framework for cosmology because it explains an enormous range of observations with just a handful of parameters. One of those parameters is the age, another is the Hubble constant, another is the density of ordinary matter, dark matter, and dark energy. Others describe the initial conditions in the early universe, the tiny density variations that seeded structure formation. The Planck satellite measured all of these parameters by analyzing the cosmic microwave background pattern. The results form a consistent picture of a flat universe dominated by dark energy, with significant dark matter and a small amount of ordinary matter, expanding at a rate that gives an age of 13.82 billion years. But there is a problem, and it is one that has cosmologists worried. When you measure the Hubble constant using the cosmic microwave background and extrapolate forward to the present day, you get a value around 67 kilometers per second per megaparsec. But when you measure the Hubble constant directly using local observations of supernovae and Cepheid variables, you get a value closer to 73 kilometers per second per megaparsec. This discrepancy is small, only about 10%, but it is statistically significant. The measurements disagree by more than the uncertainties in either method. Something is wrong. This is called the Hubble tension, and it is one of the most important unsolved problems in cosmology today. Both methods are well established. The cosmic microwave background measurements are precise and have been verified by multiple missions. The local distance ladder measurements have also been checked and rechecked using different techniques. Yet, they give different answers. If the true value of the Hubble constant is higher, closer to 73, then the universe is younger than 13.8 billion years. It might be closer to 12.5 or 13 billion years. That would create tension with the ages of the oldest stars again, though not as severe as the original Hubble crisis. Several explanations have been proposed for the Hubble tension. One possibility is that there are unknown systematic errors in one or both measurement methods. Perhaps the distance scale is not as well calibrated as we think. Perhaps the cosmic microwave background analysis makes assumptions that are not quite right. Another possibility is that the lambda CDM model is incomplete. Maybe there is additional physics at play that we do not understand. Perhaps dark energy evolves over time rather than being constant. Perhaps there are multiple types of neutrinos with masses we have not accounted for. Perhaps gravity itself behaves differently on cosmic scales than general relativity predicts. A third possibility, more radical, is that we live in a part of the universe that is not typical. The standard cosmological model assumes that the universe looks the same everywhere on large scales, a principle called the cosmological principle. But what if our local region is slightly less dense than average, or expanding slightly faster than the global average? Observations would then be biased by our location, and the Hubble constant we measure locally might not represent the true global value. This idea makes many cosmologists uncomfortable because it violates the Copernican principle, the notion that we do not occupy a special place in the cosmos. But the data might be forcing us to consider it. Resolving the Hubble tension is a high priority for observational cosmology. New telescopes and surveys are underway to measure distances and expansion rates with even greater precision. The James Webb Space Telescope, launched in late 2021, can observe Cepheid variables in galaxies much farther away than Hubble could reach. This extends the distance ladder and provides independent checks on the measurements. Other projects are using different types of distance indicators, such as the brightness of red giant stars or the properties of gravitational lensing systems, to measure cosmic expansion. The hope is that multiple independent methods will converge on a single consistent value, or reveal where the errors lie. If the tension persists, it may signal new physics. Perhaps the early universe was slightly different than our models assume. Perhaps there was a brief period of faster expansion that is not accounted for in the standard picture. Perhaps dark energy was weaker in the past and has only recently become dominant. Any of these possibilities would change the expansion history and therefore the calculated age of the universe. The current estimate of 13.8 billion years is based on the lambda CDM model. If that model needs to be revised, the age might change as well, though probably not by much. The constraints from the cosmic microwave background are very tight. Whatever the resolution, the fact that we can measure the universe's age to within 1% is a triumph of modern science. Consider the scale of the problem. We are trying to determine the age of everything, the time since existence itself began. We are confined to one planet orbiting one star in one galaxy among hundreds of billions of galaxies. Yet we can peer back across billions of light years, detecting radiation from the early universe, measuring the motions of distant galaxies, and calculating how long the cosmos has been expanding. This is possible only because the universe is governed by physical laws that operate everywhere, and those laws leave traces we can observe and measure. The age of the universe also tells us something profound about our own existence. Every atom in your body, except for hydrogen, was forged in the core of a star that lived and died before the sun formed. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of these elements were created by nuclear fusion in stars and scattered into space by supernova explosions. You are made of stardust, material that has been cycling through the cosmos for billions of years. The age of the universe sets the timescale for this cosmic alchemy. Stars needed time to form, burn, explode, and seed space with heavy elements. Galaxies needed time to assemble. Planets needed time to coalesce and develop conditions suitable for life. Life on Earth appeared remarkably quickly after the planet formed, perhaps within the first few 100 million years. But complex life took much longer. Single-celled organisms dominated for billions of years. Multicellular life emerged less than 1 billion years ago. Animals with complex nervous systems appeared only in the last few 100 million years. Human beings have existed for a tiny fraction of cosmic history, less than 100,000 years out of 13.8 billion. Our entire recorded history spans only a few thousand years, an eye blink compared to the age of the universe. We are latecomers to a cosmos that has been evolving for an almost incomprehensible span of time. Yet here we are, capable of understanding our place in that vast history. We can measure the age of the universe. We can trace cosmic evolution from the Big Bang to the present. We can calculate when stars formed, when galaxies assembled, when conditions became right for planets and life. This knowledge is recent. 100 years ago, we did not know galaxies existed beyond the Milky Way. We thought the universe might be eternal and unchanging. The discovery that the cosmos has a history, that it began in a hot, dense state and has been expanding and cooling ever since, revolutionized our understanding of reality. And pinning down the age to 13.8 billion years represents the culmination of decades of work by thousands of scientists around the world. The techniques used to measure the universe's age illustrate the power of modern astronomy. Consider the cosmic distance ladder. It starts with parallax measurements of nearby stars, using the diameter of Earth's orbit around the Sun as a baseline to triangulate distances. This works for stars up to a few hundred light-years away. The next rung uses main sequence fitting, where we compare stars in a nearby cluster to stars of known distance to calibrate their intrinsic brightness. Then come the Cepheid variables, whose pulsation periods relate directly to their luminosity. Measuring their periods and apparent brightness gives distances out to tens of millions of light-years. Finally, type Ia supernovae provide the brightest standard candles, visible across billions of light-years. Each rung of the ladder builds on the previous one. Errors accumulate as you climb, which is why calibrating each step carefully is crucial. The Hubble Space Telescope spent years observing Cepheids in galaxies far enough away to also host type Ia supernovae. This allowed direct calibration of the supernova brightness. The distances measured this way set the scale for mapping cosmic expansion. If the distance scale is wrong, everything built on it is wrong. This is why the distance ladder has been refined obsessively over decades. Small errors at the bottom compound into large uncertainties at the top. Precision at every step matters enormously. The cosmic microwave background offers a completely independent route to cosmic age that bypasses the distance ladder entirely. It relies instead on understanding the physics of the early universe. The temperature variations in the microwave background depend on how sound waves propagated through the primordial plasma. The physics of those sound waves is well understood. It is standard thermodynamics and fluid dynamics applied to a relativistic plasma. By measuring the pattern of hot and cold spots and comparing it to theoretical predictions, cosmologists can extract the age, expansion rate, and composition of the universe directly from the data. No distance measurements required. This is why the agreement between the two methods is so powerful. They are based on completely different physics. The distance ladder relies on stellar evolution, supernova physics, and measuring cosmic expansion through galaxy redshifts. The cosmic microwave background relies on plasma physics, thermodynamics, and general relativity. Yet both methods give ages around 13 to 14 billion years. The convergence is not a coincidence. It reflects the underlying consistency of physical laws and the accuracy of our models. The universe really is 13.8 billion years old. And we know this because multiple independent lines of evidence all point to the same conclusion. One of the most stringent tests of the age calculation comes from comparing it to the ages of the oldest stars. Globular clusters are ancient collections of stars that formed very early in the galaxy's history. By studying the stars in these clusters, astronomers can determine when they were born. The technique involves creating detailed models of stellar evolution that predict how stars of different masses change over time. Stars on the main sequence burn hydrogen into helium. Eventually, they exhaust their core hydrogen and begin burning hydrogen in a shell around an inert helium core. This makes them swell into red giants. The point where stars leave the main sequence and become red giants is called the main sequence turnoff, and it depends on the cluster's age. In a young cluster, only the most massive stars have had time to exhaust their hydrogen and turn off the main sequence. In an old cluster, even relatively small stars have begun to turn off. By measuring the mass and temperature of stars at the turn-off point, astronomers can calculate how long they have been burning hydrogen. This gives the age of the cluster. The oldest globular clusters in the Milky Way have ages around 12 to 13 billion years, with uncertainties of a few 100 million years. This is comfortably consistent with a universe that is 13.8 billion years old. The universe is older than its oldest stars, as it must be. But the comparison is tight. If the universe were only 12 billion years old, the oldest globular clusters would be nearly as old as the cosmos itself. That would be difficult to explain because galaxies like the Milky Way needed time to assemble before forming their first stars. The gap of 1 billion years or so between the Big Bang and the formation of the oldest globular clusters is reasonable and fits with our understanding of galaxy formation. If the age estimates were closer together, it would suggest something wrong with either the stellar age models or the cosmological age calculation. The fact that they agree within uncertainties provides mutual confirmation. White dwarfs provide another clock for measuring cosmic age. A white dwarf is the remnant of a sun-like star after it has exhausted its nuclear fuel. It no longer generates energy through fusion. Instead, it slowly cools by radiating away its thermal energy. The cooling rate depends on the white dwarf's mass and composition, and it can be calculated from physics. By measuring the temperature of a white dwarf, astronomers can determine how long it has been cooling. The coolest, oldest white dwarfs in the galaxy have been cooling for about 12 billion years. This means they formed within 1 billion or 2 years after the Big Bang, consistent with the universe's age of 13.8 billion years. Metal-poor stars provide yet another age constraint. The very first stars formed from gas that contained only hydrogen, helium, and traces of lithium from the Big Bang. These stars produced heavier elements through fusion and scattered them into space when they died. Subsequent generations of stars formed from gas increasingly enriched with metals, a term astronomers use for all elements heavier than helium. The most metal-poor stars we observe today formed from gas that was only slightly enriched, meaning they must be very old. Measuring their composition and comparing it to models of chemical enrichment gives ages consistent with 13 billion years or more. Again, the universe is old enough to accommodate these ancient stars. Distant galaxies offer a different perspective on cosmic age. When we look at galaxies billions of light years away, we are seeing them as they were billions of years ago, because light takes time to cross that distance. The farther we look, the farther back in time we see. Telescopes can now observe galaxies that existed when the universe was less than 1 billion years old. These early galaxies appear small and irregular, different from the large spiral and elliptical galaxies we see nearby. They represent an earlier stage of galaxy formation when the universe was young and structure was just beginning to assemble. The existence of these galaxies at known distances and redshifts provides a consistency check on cosmic age and expansion history. Redshift is the key to understanding how far back in time we are looking. As light travels through expanding space, its wavelength stretches. This causes the light to shift toward the red end of the spectrum, hence the term redshift. The amount of redshift depends on how much space has expanded since the light was emitted. A galaxy with a redshift of 1 has light that has been stretched by a factor of 2, meaning space has doubled in size since that light left the galaxy. A galaxy with a redshift of 10 has light that has been stretched by a factor of 11, meaning space is 11 times larger than when the light was emitted. By measuring redshifts and using models of cosmic expansion, astronomers can calculate how long ago the light left the galaxy. The James Webb Space Telescope has observed galaxies with redshifts around 13 or more, meaning we are seeing them as they appeared less than 500 million years after the Big Bang. These are among the earliest galaxies in the universe. Their existence tells us that structure formation began quickly after the Big Bang. Stars and galaxies were assembling when the universe was only a few % of its current age. This rapid formation of structure is a key prediction of the Lambda CDM model, and observations confirm it. The galaxies are there, shining in the distant past, exactly when and where the models predict. One of the surprising aspects of the universe's age is how much time remains ahead. The universe is 13.8 billion years old now, but it will continue expanding forever. Dark energy, which makes up most of the universe, causes the expansion to accelerate. This means galaxies will move apart ever faster, and eventually, distant galaxies will recede so quickly that their light will never reach us. Billions of years from now, observers in the Milky Way will see a much lonelier cosmos. Other galaxies will have disappeared beyond the horizon. The night sky will contain only the stars of our own galaxy and the handful of nearby galaxies gravitationally bound to us. The sun will continue burning for about another 5 billion years. It will eventually exhaust its hydrogen fuel and swell into a red giant, engulfing the inner planets, including Earth. After a few 100 million years as a red giant, it will shed its outer layers and collapse into a white dwarf. This remnant will slowly cool over trillions of years, eventually becoming a black dwarf, a cold, dark cinder. But even after the sun dies, the universe will continue. Stars will keep forming in galaxies for hundreds of billions of years, as long as there is gas to fuel them. Eventually, though, gas will run out. Stars will die and not be replaced. Galaxies will become dark graveyards of stellar remnants. On even longer timescales, the universe will become increasingly empty and cold. Protons, the building blocks of atomic nuclei, might decay over immense spans of time, turning all matter into radiation. Black holes will evaporate through Hawking radiation, a quantum process that causes them to slowly lose mass and eventually disappear. The last black holes will evaporate in 10 to the 100 years, a 1 followed by 100 zeros. After that, the universe will contain only photons and other particles spreading ever farther apart in an endless void. This is the heat death of the universe, a state of maximum entropy where nothing interesting can happen anymore. But that is far, far in the future. The current age of 13.8 billion years is early in cosmic history. We live in an era when stars still shine, when galaxies still contain gas and dust, when planets can form and life can emerge. This epoch will last for hundreds of billions of years. Humanity's entire existence so far occupies only the tiniest sliver of cosmic time. If the history of the universe were compressed into a single year, humans would appear in the last few seconds before midnight on December 31st. We are newcomers, but we arrived at a time when the universe is full of structure and activity. Our ability to calculate the universe's age reflects a broader achievement. We have developed a scientific framework that allows us to understand the cosmos on its largest scales and trace its history back to the earliest moments. This framework, the Lambda CDM model, successfully explains an enormous range of observations. It predicts the pattern of temperature variations in the cosmic microwave background. It accounts for the abundances of light elements produced in the first few minutes. It explains the distribution of galaxies across space. It matches the observed acceleration of cosmic expansion. It gives an age consistent with the oldest stars and globular clusters. No competing model can match this breadth of successful predictions. Yet the model is based on mysteries. We do not know what dark matter is. We have not detected dark matter particles directly despite decades of searching. We infer their existence from gravitational effects, but their fundamental nature remains unknown. Are they a new type of particle predicted by theories beyond the standard model of particle physics? Are they something even stranger, perhaps related to extra dimensions or modifications of gravity? Multiple experiments are underway to detect dark matter particles or rule out certain possibilities. So far, the question remains open. Dark energy is even more mysterious. The simplest explanation, that it represents the energy of empty space, raises severe theoretical problems. Quantum field theory predicts that empty space should have an enormous energy density, far larger than what we observe. Why is the actual value so much smaller? This is called the cosmological constant problem, and it is one of the deepest puzzles in theoretical physics. Some physicists think dark energy is not constant but evolves over time, a possibility called quintessence. Others suggest that general relativity needs to be modified on cosmic scales. Many possibilities have been proposed, but none are conclusively supported by data. Despite these mysteries, the Lambda CDM model works. It fits the data remarkably well. The age of 13.8 billion years emerges from fitting this model to the cosmic microwave background observations and other measurements. If the model is wrong in some fundamental way, the age calculation might change. But any new model will have to match all the same observations that Lambda CDM explains. That severely constrains how different the new model can be. Even if dark matter and dark energy turn out to be something unexpected, the age of the universe is unlikely to change by more than a few percent. The observational constraints are too tight. The Hubble tension remains the most significant challenge. If the local measurements of the expansion rate are correct and the cosmic microwave background measurements are also correct, then something is missing from the standard model. Perhaps early dark energy, a component that was significant in the early universe but has since decayed away, affected the expansion history. Perhaps there are interactions between dark matter and dark energy that we have not accounted for. Perhaps gravity is stronger or weaker on certain scales than general relativity predicts. Cosmologists are exploring all of these possibilities, testing them against observations. New data will be crucial. The next generation of cosmic surveys will map billions of galaxies, measuring their distances and redshifts with high precision. Projects like the Vera Rubin Observatory's Legacy Survey of Space and Time will catalogue the entire visible sky repeatedly, tracking how the universe changes over time. Gravitational wave detectors are becoming sensitive enough to measure cosmic expansion using colliding black holes and neutron stars as standard sirens, providing yet another independent measurement of the Hubble constant. Space missions are being planned to study the cosmic microwave background with even greater precision. The next decade will bring a flood of new data. These observations will refine the age of the universe and test the lambda CDM model in new ways. If the Hubble tension persists and cannot be explained by measurement errors, it will point toward new physics. If it resolves in favor of one method or the other, we will have a clearer picture of cosmic expansion. Either outcome advances our understanding. Science progresses by finding discrepancies and resolving them, either by improving measurements or by revising theories. The current tension is a sign of progress, not failure. It means our measurements have become precise enough to reveal subtle inconsistencies that demand explanation. The philosophical implications of the universe's age are worth contemplating. For most of human history, people lived without any sense of cosmic time. The universe seemed eternal and unchanging. The sky was a fixed dome of stars that wheeled overhead but did not evolve. Then, beginning in the 19th century, scientists realized that Earth itself has a deep history. Geology revealed layers of rock laid down over millions of years. Fossils showed that life has changed dramatically over time. Evolution explained how species arise and go extinct. The Earth became a dynamic system with a past that could be studied and understood. In the 20th century, this historical perspective expanded to encompass the entire cosmos. The universe has a history just as Earth does. It began in a hot, dense state and has been evolving ever since. This realization transformed our view of reality. The universe is not a static stage on which events play out. It is a dynamic entity that changes over time. Galaxies form and evolve. Stars are born and die. Elements are created and scattered. Structure emerges from chaos. Understanding the age of the universe means understanding our place in this grand story. We are part of an ongoing process of cosmic evolution that has been unfolding for 13.8 billion years. This perspective changes how we think about existence. We are not separate from the universe. We are made of material forged in stars. We are structures assembled by the same gravitational forces that form galaxies. We are products of evolution, shaped by conditions that arose through cosmic history. The atoms in your body are older than Earth. They have been cycling through the cosmos for billions of years, part of countless stars and planets before finding their way into you. When you die, those atoms will disperse and become part of other things. You are a temporary pattern in the flow of matter and energy through space and time. Yet here you are, capable of understanding that flow. You can measure the age of the universe. You can trace the history of the cosmos from the Big Bang to the present. You can calculate when stars formed, when galaxies assembled, when planets coalesced. This ability to comprehend cosmic history is itself remarkable. We are the universe becoming aware of itself. We are matter organized in such a way that it can reflect on its own origins. This self-awareness emerged only recently in cosmic history, but it represents something genuinely new. As far as we know, humans are the first and only beings capable of measuring the age of everything. Other civilizations might exist elsewhere in the universe, and they might also have developed cosmology and calculated their universe's age. We do not know. The question of extraterrestrial intelligence remains open. But whether we are alone or not, the fact that intelligence arose at all is significant. The universe is not just a collection of particles and forces evolving mechanically. It contains structures complex enough to understand themselves. Life emerged. Consciousness arose. Science developed. These are all part of cosmic evolution, just as much as galaxy formation and star death. The age of the universe sets the timescale for all of this, including the emergence of beings capable of measuring that age. 13.8 billion years is both an unimaginably long time and, from another perspective, surprisingly short. It is long enough for galaxies to form, for stars to go through multiple generations, for planets to develop, and life to arise. But it is short compared to the future. The universe will exist for far longer than it has already. We live in the early universe, the bright era when stars still shine. The universe will spend most of its existence in the dark era, after star formation has ceased and galaxies have faded. Our moment is special, not because we are central to the cosmos, but because we happen to exist during a brief window when conditions allow for complexity and life. This raises the question of whether the universe's age is fine-tuned for life. If the universe were much younger, there would not have been enough time for heavy elements to form and planets to develop. If it were much older, stars might have already burned out. Is the age of 13.8 billion years somehow necessary for our existence? This is a version of the anthropic principle, the idea that the universe has the properties it does because those properties allow for observers. If the universe were different, we would not be here to notice. This is logically true, but philosophically contentious. It feels like explaining the universe by reference to our own existence, which seems backwards. Yet there is something to it. The physical constants and initial conditions of the universe do appear to be finely tuned. If the strength of gravity were slightly different, stars might not form. If the electromagnetic force were stronger or weaker, chemistry would not work. If the density of the early universe were a bit higher or lower, structure might not emerge. The fact that all these parameters fall within the narrow ranges needed for life and complexity is striking. Some physicists argue that this points toward a multiverse, where countless universes exist with different physical constants, and we inevitably find ourselves in one where the constants allow for life. Others argue that we simply do not understand why the constants have the values they do, and future theories will explain it without invoking multiverses or anthropic reasoning. Regardless of the explanation, we can measure the age of the universe we inhabit, and that age is 13.8 billion years. This number represents one of humanity's greatest intellectual achievements. It required developing general relativity to understand gravity and space-time. It required building telescopes capable of detecting faint radiation from the edge of the observable universe. It required launching satellites to measure the cosmic microwave background from space. It required understanding nuclear physics to explain how elements form in stars. It required computer simulations to model the evolution of structure. All of these disciplines came together to produce a single number, an answer to one of the oldest questions: how long has the universe existed? The journey to this answer took a century of work by thousands of scientists. Edwin Hubble discovered cosmic expansion in the 1920s. George Gamow predicted the cosmic microwave background in the 1940s. Arno Penzias and Robert Wilson discovered it accidentally in 1965. John Mather and George Smoot led the COBE satellite mission in the 1990s, mapping the microwave background and confirming its blackbody spectrum. The WMAP satellite refined the measurements in the 2000s. The Planck satellite pushed precision even further in the 2010s. Each step built on previous work, narrowing uncertainties and testing the model. At the same time, other astronomers were working on the cosmic distance ladder, measuring Cepheid variables, calibrating supernova brightnesses, and mapping the expansion of space. Wendy Friedman and colleagues spent years using the Hubble Space Telescope to measure distances to galaxies. Adam Rees, Saul Perlmutter, and Brian Schmidt discovered cosmic acceleration using distant supernovae, work that earned them the Nobel Prize in 2011. Alan Sandage devoted his career to measuring the Hubble constant, refining estimates over decades. These efforts and many others converged on an age of approximately 13.8 billion years. The precision of this measurement is astonishing. We are not talking about an order of magnitude estimate. We are not saying the universe is between 10 and 20 billion years old. We are saying it is 13.82 billion years old, give or take 40 million years. That is a fractional uncertainty of less than 1%. For comparison, the age of Earth is known to about 1% as well, roughly 4.54 billion years, with uncertainties of tens of millions of years. We know the age of the entire universe as precisely as we know the age of our own planet. That is extraordinary. This precision comes from the cosmic microwave background. The pattern of temperature variations contains so much information, and it has been measured so carefully that the parameters of the universe can be extracted with remarkable accuracy. The Planck satellite observed the microwave background in 9 frequency bands, allowing scientists to separate the primordial signal from contamination by dust and other sources in our galaxy. The data was analyzed using sophisticated statistical techniques and compared to millions of simulated universes with different parameters. The parameters that best match the observed pattern are determined with high confidence. But precision is not the same as accuracy. We can measure something very precisely and still be wrong if there are systematic errors or if the model we are using is incorrect. The age of 13.8 billion years assumes that the lambda CDM model is correct. If dark energy behaves differently than we think, if there are additional components to the universe we have not accounted for, if general relativity needs to be modified, then the age could be different. The Hubble tension hints that something might be missing from the standard model. Until that tension is resolved, there remains some uncertainty about whether 13.8 billion years is the true age. Nevertheless, the convergence of independent methods gives confidence. The cosmic microwave background, the expansion rate, the ages of the oldest stars, the abundances of light elements, the distribution of galaxies, all of these point to an age around 13 to 14 billion years. Even if the exact number shifts slightly as measurements improve or the model is refined, the ballpark is secure. The universe is not a trillion years old. It is not a million years old. It is billions of years old, and that timescale is consistent across multiple independent lines of evidence. We can trust the basic picture, even if details remain to be worked out. The universe's age also tells us about the future. If we know how old the universe is and how fast it is expanding, we can extrapolate forward. Dark energy ensures that the expansion will continue accelerating. Galaxies will move apart ever faster. Eventually, the expansion will become so rapid that light from distant galaxies will never reach us. The observable universe, the region of space from which light has had time to reach us since the Big Bang, will shrink. Paradoxically, the universe as a whole keeps expanding, but the part we can see will become smaller. Distant galaxies will redshift to invisibility as they accelerate beyond the horizon. Stars will continue forming for a long time, but not forever. Gas gets locked up in dead stars, black holes, and planets. The supply of raw material for star formation gradually depletes. Within 1 trillion years, star formation will have mostly ceased. Galaxies will become dark, filled with brown dwarfs, white dwarfs, neutron stars, and black holes. The universe will enter a long twilight, dimming slowly over incomprehensible spans of time. But this is so far in the future that it is hard to relate to. 1,000,000,000,000 years is more than 70 times the current age of the universe. Compared to the time that has passed, the time ahead is almost endless. For now, we live in a universe full of light and activity. Galaxies are forming stars. Planets are coalescing. Life is arising on some of those planets, and perhaps intelligence is emerging elsewhere as it has here. This is the era when the universe is interesting, complex, and dynamic. We are fortunate to exist during this window. We are also fortunate to exist at a time in human history when the tools and knowledge needed to measure cosmic age are available. A few centuries ago, this would have been impossible. A few centuries from now, it will be trivial. We live at the moment when humanity is first answering these ancient questions. Measuring the age of the universe is more than an academic exercise. It is an attempt to understand our origins, to situate ourselves in time and space, to grasp the scope of existence. Knowing that the universe is 13.8 billion years old changes how we think about ourselves. We are part of a cosmic story that began long before us and will continue long after we are gone. Our individual lives span less than a century, but we are connected to a history that spans billions of years. The atoms in our bodies were forged in stars that died before the sun was born. We are made of ancient stardust, recycled matter that has been part of the universe since nearly the beginning. This perspective can be humbling. We are insignificant specks in an unimaginably vast cosmos. Our planet is a tiny rock orbiting an ordinary star in an unremarkable galaxy. We have existed for an eye blink compared to cosmic time. Nothing we do will matter on the scale of billions of years. The universe will continue whether we are here or not. Yet this same perspective can be empowering. We are part of the universe, made of the same material and governed by the same laws as everything else. We are the universe exploring itself. Through us, the cosmos has become aware of its own existence. We can measure its age, trace its history, and predict its future. That is remarkable. This is how science works. We make observations, develop models to explain them, test those models with new observations, and refine or replace the models as needed. The Lambda CDM model is the best explanation we have for cosmic history, but it is not the final word. Future observations might reveal new phenomena that require revising the model. Dark energy might turn out to be something other than the cosmological constant. Dark matter might be detected directly, changing our understanding of its properties. Gravitational waves might provide new insights into cosmic expansion. The age of 13.8 billion years might be refined or adjusted as new data comes in. But the basic picture is solid. The universe began in a hot, dense state about 13 to 14 billion years ago. It has been expanding and cooling ever since. Structure emerged as gravity pulled matter together into galaxies, stars, and planets. We live in one of those galaxies, orbiting one of those stars, on one of those planets. We have existed for only a fraction of cosmic history, but we have been here long enough to figure out where we came from and how old everything is. That knowledge is part of our inheritance as members of an intelligent species. It is something we can pass on to future generations, along with the tools and methods for continuing to explore. The age of the universe connects to deeper questions about existence. Why does anything exist at all? Why is the universe the way it is, and not some other way? Why does it follow mathematical laws that we can understand? These are philosophical and perhaps unanswerable questions, but they naturally arise when contemplating cosmic origins. Science can tell us how the universe began and how it has evolved, but it cannot fully explain why there is something rather than nothing. Perhaps that question lies beyond science. Perhaps it will always remain a mystery. Or perhaps future discoveries will shed light on even these fundamental puzzles. For now, we have an answer to one of the great questions. The universe is 13.8 billion years old. This number is based on careful observations, rigorous analysis, and a deep understanding of physical laws. It is not a guess. It is not speculation. It is a measurement, and it represents the culmination of a century of work by astronomers and cosmologists around the world. The number might be refined as measurements improve, but the basic answer is secure. We know the age of the universe. If this journey through cosmic time has sparked something in you, consider what it means to live during an era when such knowledge is possible. We stand at a unique moment in history when the tools exist to answer questions our ancestors could only wonder about. Countless mysteries still await, hidden in the data yet to be gathered, the observations yet to be made, the theories yet to be imagined. The universe is 13.8 billion years old, and yet its story is far from finished. Your awareness of that story, your ability to comprehend these vast stretches of time and space, is itself a small miracle born of that ancient cosmos. Leave your thoughts below, share what resonates, and until next time, remember that you are made of atoms forged in the hearts of stars that lived and died billions of years before you were born, woven into the unfolding tapestry of a universe still revealing its deepest secrets.